This video is for the 2017 Chemistry Challenge question number 2. So I'm going to go through each part of this question with some tips for how you can work them out. So once I've gone through a couple of these questions, you might want to stop the video, so pause it and then have a go at the questions yourself using the advice I've given you, and then you can check your answers, because some parts of the question rely on you having the previous part right. Alright, so let's start with A part 1. 1 mole of ethane reacts with 1 mole of bromine to give bromomethane. Write a balanced equation for this reaction. I think we can all do that, that's not a problem. How would you classify this reaction? I think you should be able to classify the reaction as well. And the reaction between ethane and bromine requires light and does not proceed in the dark. The light is needed to break a bond in the start the reaction. I think you can have a good attempt at that as well, given what you've learned in year 12. Okay, now down here. All right, so when ethane reacts with bromine, any one of the 6 hydrogen atoms can be replaced. The symmetry in the molecule of ethane means that all 6 of these hydrogen atoms are equivalent, and so there is only one possible product no matter which hydrogen is replaced. So what that means is, if you draw out a molecule of ethane, it looks like this. And you can see that all of those hydrogen atoms are all exactly the same. They're all equivalent to each other. They're all in exactly the same environment. So you could even go around and you put a little 1 after each one to show you that they're all exactly the same. Now, if I had a different molecule, let's say I had propane, like this, you should be able to see now that not all of these are equivalent. Okay, but you should be able to decide which ones are equivalent. Now, obviously these 3 here, these are all going to be the same as each other. All right, which are different to these 2. But these 2 are the same because they're bonded to the same carbon atom. All right, now we need to decide if these 3, are these 3 in a different environment to the 2 or not? Well, because the molecule is symmetrical down the middle, these 3 hydrogen atoms are the same as these 3, so they would all be H1s as well. So in propane, there are actually only 2 different types of hydrogen atom. All right, and that's what this paragraph here is talking about. So with larger alkanes, there is often the possibility of forming different structural isomers of the bromo-alkane product, depending on which hydrogen atom is replaced by a bromine atom. In the bromination of methyl butane, 4 different bromo-alkanes can be formed. So, assuming that all the hydrogen atoms present in methyl butane are equally likely to be replaced. Okay, so you might start thinking now, well, you know, I've got secondary positions and tertiary positions and primary positions. Okay, don't worry about that for this question. So first of all, you just need to decide how many different kinds of hydrogen atom there are, and assuming that each one can be replaced equally likely, which of these 4 is going to come out in the smallest proportion. So to give you an example of how that would work is, if we go back to my example of propane, now I can form 2 different isomers if I react that with HBr. I can form either this bromoalkane or this bromoalkane. Okay, by adding it onto, so here I've added it onto the terminal carbon, and here I've added it onto the middle carbon. Now, if I assume that all of them are equally likely to be replaced, which is not the case, but it's just an assumption I'm going to make for now, what would be the relative proportions of these? Well, to form this one, I've got 1, 2, 3, 4, 5, 6 possible positions. To form this one, I've got only 2 possible positions. So assuming that each one could be replaced equally, I would get these 2 products in a 6:2 ratio. So that's how you answer this question. So once you've worked out which one will come out in the smallest proportion, the next question is just asking you to work out how likely all of them are to be formed, and you just do that in the same way that I've just shown you. Okay, so that's probably a good place to pause the video before moving on to the next part. All right, so question D is just a bit of maths. If you read the explanation, it's fairly straightforward how to do that. And then we move on to E. By considering the symmetry of the following alkanes or otherwise, determine how many different bromo-alkane structural isomers could be formed by replacement of one hydrogen atom with a bromine. So in this, you just need to decide, well, if I replace one hydrogen atom with a bromine atom, how many isomers can I form? So going back to my propane example, I was able to form 2 isomers. All right, and that's all you need to do here. But obviously, you know, some of these molecules are highly symmetrical, so you need to be really careful about deciding how many different kinds of carbon atom there are. So, for example, down here, this carbon atom here, if I was to add on a bromine here, okay, that would be the same as adding a bromine here, and it would be the same as adding a bromine here, and it would be the same as adding a bromine here. Okay, so obviously this one's a little bit more tricky, but have a go at that. All right, so once you've done that, now we're going to get into the sort of, that's the warm-up part of the question, and now we're going to get into the proper part of the question. So we're going to be thinking about this molecule for the next few parts. All right, so how many, once you've read the little introduction, how many different structural isomers of the bromo-alkane E could possibly be formed by replacing one hydrogen in 1,3-dimethyl adamantane with bromine? So you need to decide in here how many different types of hydrogen atom are there. Okay, so obviously the hydrogen atoms bonded to this carbon are going to be the same as the hydrogen atoms bonded to this carbon. All right, so that's one possible type of hydrogen atom. So if I add a bromine here or a bromine here, I get the same isomer because it's symmetrical. So you're going to have to have a good think now. All right, you might want to mark on all the possible different locations of hydrogen atoms and where they can be replaced with bromine atoms, and then try and work out how many of them are different from the others. Okay. So in the synthesis of memantine in the laboratory, only one structural isomer of E was formed. By considering the information earlier in this question, the information earlier in this question is referring to this information here, okay, which should make it fairly obvious. Draw the structure of this isomer. So in the answer booklet, it's got this structure, and you just need to add on where the bromine atom will be added, which I think is fairly straightforward. Okay, so once we've done that, we can move on to the next part over the page. So this is quite a common way of asking questions in this paper. What they'll do is they'll give you a reaction that you haven't seen before, all right, and they'll give you the generalized starting material, so any alkane R with a bromine atom attached to one of the carbon atoms. It will give you the reactant and the conditions, and then the generalized product. And then you have to use this generalized version of the reaction to work out a specific answer. Okay, so the conversion of E into memantine is shown below. By modifying the structure shown in your answer booklet, draw the structures of compound F, memantine, and the anion G-. So to work out the structure of compound F is fairly straightforward because you've already decided which carbon atom the bromine is bonded to. All right, so then you can just, whichever one it is, let's imagine just for argument's sake it was this one here. It's not, but let's imagine it is. Okay, then what you then do is you then replace all of this with R. Okay, and then you're doing this reaction here where really the bromine, Okay, so the bromine is going to get replaced with all of this stuff. So in your structure, you're just going to replace the bromine with all of this stuff. So that's fairly straightforward to do F, because that is the exact same reaction. All right. Now we have a slightly more complicated situation, because you're just given a reactant and you have to try and work out what the product is without knowing what type of reaction it is. Okay, so I'm going to tell you what type of reaction it is. Okay, so this is, so to go from here to here, this is base, catalyzed, amide, hydrolysis. Okay, so it's a base because this is a base. It's amide because this type of structure up here, this is an amide. Okay, and hydrolysis is generally will be done in water, obviously, and it will involve the breaking of a bond. Okay, but if you look up base catalyzed amide hydrolysis, then you'll see what that looks like. I can send you a link to the mechanism for that. Actually, I'm not sure if it would be called base catalyzed. I don't think the base is necessarily reformed at the end. I need to think about that. But it's definitely hydrolysis of an amide in basic conditions. All right. So looking that up should be able to get you memantine and the anion G minus. Okay. So once you've done that, you'll probably want to check that you've got the answers to those correct. So the drug, which I can't pronounce, is used for the treatment of schizophrenia and anxiety. The synthesis of that drug uses 1,3-dibromopropane as one of the starting materials. Draw the other structural isomers of dibromopropane. Okay, I think you should be able to do that. If 2 moles of bromine are added to 1 mole of propane and the mixture subjected to light, a mixture of these dibromopropanes can be produced. Calculate the percentage of 1,3-dibromopropane that would be produced in this mixture if all the hydrogen atoms were equally likely to be replaced in this reaction. So this is going back to what we were thinking about before. So I've got, this is propane, all right, but now I'm going to add 2 bromine atoms to it. So I'm going to make this molecule. Okay, because that's 1, 3. And the question is asking us, calculate the percentage of 1,3-dibromopropane that would be produced in this mixture if all the hydrogen atoms were equally likely to be replaced in this reaction. So, you're obviously going to get your 1,3-dibromopropane and any other isomers of dibromopropane that you can think of. Now, to work out the percentage, if they're all equally likely to be replaced, the hydrogen atoms, you could either work out all the different possible structures that could be formed, which might take a long time, or you can just think about it in stages. So think, well, all right, so in order to form this particular compound, I need to first replace one of these. Okay, so how likely is it that I replace one of those? All right, now once I've replaced one of those with the bromine, okay, now I need to obviously replace one of these 3. So how likely is it that I replace one of these 3? Okay, so once you've done that one, we can move on to this one. Unfortunately, no 1,3-dibromopropane is produced at all when this reaction is attempted in the laboratory, as the reaction favours other isomers. all right? However, another hydrocarbon does react with bromine to give 1,3-dibromopropane. This hydrocarbon contains 85.63% carbon by mass, so this is an empirical formula question. All right, it's fairly easy empirical formula question, much easier than the kind that I would give you, because there's only 2 atoms in it. Now, once you've done it, you're going to draw the structure of H, and it's going to make sense. So your empirical formula is going to suggest to you what the structure is. But that structure will not produce 1,3-dibromopropane. You need to think very carefully about what other structures you can get from your empirical formula for H. All right? And you should be able to fairly easily work out what kind of reaction that is. Okay? Right, so once you've done that one, we can move on to the synthesis of this schizophrenia drug that we're talking about. Okay, so this is the synthesis. Okay, looks a little bit scary. Don't worry about it. It's not too scary. Draw the structures of compound I and reagent J. Okay, so compound I is the reaction between 1,3-dibromopropane that we've been talking about, and then this big thing here. Okay, but this big thing here, these benzene rings and this big 1, 2, 3, 4, 5, 6, 7-membered ring here, that's just there, just to look scary. Okay, but really all that this is this. Okay, and this is a nucleophile. So if you react this with this, that's just a nucleophilic substitution reaction. Okay, so remind yourself of nucleophilic substitution, and you should be able to work out fairly easily what compound I is. In fact, it should be fairly obvious looking at this what it is. Okay, because as a hint, I've got 1, 2, 3 carbon atoms in my 1,3-dibromopropane. Can I see anywhere in here where I've got a chain of 3 carbon atoms? Yes. All right, so that should give you some hints as to what compound I is. And then in terms of what compound J is, well, compound J is going to have something to do with this extra bit here, isn't it? So it's going to have this extra bit here. And the reaction to form this is the same reaction to form compound I. All right. Remember, 1,3-dibromopropane can undergo nucleophilic substitution twice because it's got 2 bromine atoms. Okay. Now, once you've done that, you probably want to pause it there, do those questions, make sure you got those right, and then we move on to the final part. So 1,3-dibromopropane is used in a different synthesis to make this drug, okay, which is used to treat pain and anxiety. All right. Now, the carbon atoms in this ethoheptazine, all right, which are not already present in this, come from either 1,3-dibromopropane or from ethanol. And we're told that no carbon-carbon bonds are broken during this synthesis. So if I look at this ethoheptazine, okay, I've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got 16 carbon atoms. All right. Now if I look at my starting material, I've got 6, 7, 8, 9, 10, 11 carbon atoms. All right. Now in dibromopropane, I've got 3 carbon atoms. And in ethanol, I've got 2 carbon atoms. So if I do 11 plus 3 plus 2, I get 16. So all of the carbon atoms in this product come from this, this, and this. All right. Now, in the answer book, circle the 3 carbon atoms in ethoheptazine which come from 1,3-dibromopropane. Now, you don't need to know what's happening at each stage in order to know which 3 carbon atoms are from dibromopropane. Okay? This benzene ring is obviously, must be this benzene ring here. Okay? So, from that, you should be able to work out this nitrogen atom is going to be either this one or this one. It's going to be one of these two. So you can work out from the length of the carbon chain which one it is. And then that should allow you to decide which carbon atoms are from dibromopropane. It should also be fairly obvious which are the 2 carbon atoms from ethanol, which is required for the next question. All right, because remember, these 2 carbon atoms are bonded to each other, and that bond isn't broken, so it's fairly straightforward. All right, you don't need to worry about what's actually going on. The synthesis of ethoheptazine takes 5 steps. In the first step, the starting material is deprotonated to give K-, which is a carbanion. Draw the structures of carbanion. K-, so that's 1, compound L, 2, cation N+, 3, and compound N4. Right, so now unfortunately you do need to know what's happening. Okay, so this is how you do this question. You're using a base to remove a proton, so you need to decide which is the most acidic proton. All right, that should be a fairly straightforward decision. That will give you carbanion K-. All right. Now remember, a carbanion is something like R. That's a secondary carbanion. All right. Now that is a nucleophile. So that again is going to do nucleophilic substitution with your 1,3-dibromopropane. All right. So nucleophilic substitution with that should give you compound L. Now I'm going to give you one hint here, all right? So L to M+, this step here, that's a ring forming process. Okay, so this ring here, all right, that is formed in that step. All right, now M+ to N, all right, so that should give you M+. To work out what compound N is, you need to look carefully at what the other product is. So you've got this molecule here, all right, and you've got a bromide ion. So what you're going to do is you're going to remove from this, you're going to remove CH3+. All right, so once you've got the structure of M+, it should be fairly easy to decide which CH3+ you're going to lose from that structure to give you compound N. All right, and there you have it.